So I would like to discuss some facts and some recent results on FRB emission mechanisms. And this is work that has been done thanks to the great collaboration of a couple of graduate students at Columbia, Alia and Navin, and Ilya Plotnikov, a postdoc I had the luck to collaborate with on this FRB-related project. So let's get started. Why do we need something special for FRBs? Why do we need a coherent emission mechanism for FRBs? One can compute, given typical FRB parameters, the brightness temperature, as you're all aware, and the brightness temperature is huge, 10 to the 35 Kelvin, not accounting for relativistic effects, which can alleviate the problem a little bit, but this is significantly larger orders of magnitude, many orders of magnitude than the Compton temperature, which implies that there is no particle population that can sustain such a high brightness temperature unless the radiated power is coherent, which means that given the power of a single electron and n number of electrons, the total power output is n squared times the power of a single electron rather than just linear with the number of electrons as one would expect for any incoherent radiation process. And historically, 3 radiation processes have been invoked for coherent emission by the father of coherent emission in space physics and astrophysics, Melrose in '86, even Ginzburg before that. The 3 mechanisms are listed here very broadly, and many people in the FRB community have worked on one on the other, so I will let you put yourself in the box that you belong to. The antenna mechanism, the basic idea here is that you have bunches of charge localized both in space and in momentum, and they are effectively acting as a gigantic macro charge, radiating coherent emission because they are clustered together in space and in momentum. And the question here is, first, how do the bunches get formed in the first place? And the second, the bunches, due to the effect of the emission itself, can be dispersed in space. So you're losing the bunch coherence in space, and something needs to intervene in order to sustain the process for a longer time because it's self-destructive. The second possibility is the possibility of a reactive instability. This is a general idea of a beam plasma instability. You have localization in momentum space, not necessarily in physical space, and this leads automatically, self-consistently to self-bunching also in physical space and a phase-coherent wave growth. This is, for example, that has been invoked for decades as a potential explanation for the pulsar coherent radio emission with a beam of higher energy particles interacting with a population of lower energy particles. This will produce bunches in space and subsequent coherent radio emission. Still, one needs to explain what produces the momentum localization in the first place and what can sustain the momentum localization against the self-destruction that the instability itself will will have as a part of its self-consistent evolution. And finally, the Maser instability, or any Maser process which relies on a population inversion with a growth that generally corresponds to a negative absorption index. And two Maser have been discussed, I would say, in the last couple of years in the context of FRBs. Synchron Maser in weakly magnetized plasmas, and I will refer you to Eli's talk for that. And also the synchron Maser in magnetized shocks, which I'm going to focus for most of the presentation today. Again, for the Maser, one needs to explain where the population inversion is coming from and what sustains the population inversion, which would naturally be destroyed by the release of the electromagnetic wave itself. So for approaching this problem, in most of what I will be presenting afterwards, I rely on a self-consistent method of capturing the interplay between charged particles and electromagnetic fields. This is the so-called particle-in-cell method. It virtually relies on no assumptions, so it can capture really this interplay from first principles. It relies on the Lorentz force for pushing the particles and on Maxwell's equations for solving for the electric and the magnetic fields. So all the frequencies and the wavelengths that you can accommodate on your numerical grid are properly resolved with all of the electromagnetic classical physics that enters into the problem. And as I'm sure you're aware, this opens a computational challenge because typically the plasma scales resolved by the particle in cell simulations are much smaller than astronomical scales. I'm giving here some numbers. The characteristic length is the so-called plasma skin depth. It's 10 to the 5 centimeters. The characteristic time is the so-called inverse plasma frequency. It's 10 to the minus 5 seconds. So these are typically, for a density of 1 particles per cc, much smaller than astrophysical scales. And this is still true also for the very short duration of FRBs. So the emphasis really for this type of simulation should be in getting an answer that is a steady state answer, because even a millisecond duration FRB, from the point of view of the plasma physics, is a quasi-steady state process. Before getting into the shock maser that I would like to spend most of the time on, I anticipate a little bit Yuri Lubarsky's talk by showing that a recent proposal has been put forward as well for explaining or for invoking a mechanism of coherent emission from magnetic reconnection. So magnetic reconnection is a process of annihilation of magnetic fields that happens when you happen to have a configuration with magnetic field lines of opposite polarity separated by a relatively narrow region. And in particular, the regime that might be most relevant for fast radio bursts is the regime in which the so-called magnetization parameter, that is the ratio of the magnetic energy density to the rest mass energy density, is much larger than unity. This is called relativistic reconnection. And simulations have shown, and this is a simulation run by Navin, that the reconnection process in this regime is highly dynamical. So this is the reconnection layer. You have this constant formation of structures that we call magnetic islands or plasmoids. They're growing, they're smashing into each other. This is a continuously dynamical process. And associated with that, you have, as you might see here, in addition to the mean pointing flux that is carrying magnetic energy and particles into the reconnection region, you have some escaping waves as well that are here evidenced by the reddish and yellowish color on the right and by the bluish color on the left. So the reconnection process by itself is capable of producing waves, escaping waves. In this case, these are magnetosonic waves. These magnetosonic waves could eventually convert to electromagnetic waves and giving rise to coherent electromagnetic emission. This is the same plot as on the left, but subtracted the mean pointing flux carried into the reconnection layer. So it's just to emphasize the escaping wave component. This has been invoked by Yuri and by Sasha Filippov and others as a mechanism to power the Crab radio emission. The efficiency that has been derived with peak simulations is of order 10 to the minus 4. Time average is of order 10 to the minus 4 of the available magnetic energy. So these are the numbers we are fighting with, or we have to deal with for a reconnection-based model. And now most of what I will be focusing on is on a very biased view of the synchron maser instability in shocks around magnetars. So this is the scenario that Ben and Andrei have already discussed yesterday. Strongly relativistic magnetar flare can drive a shock into either the magnetar wind, in which case the shock will be running into an electron-positron plasma, or into a prior electron-positron potentially enriched proton shell ejected in a previous magnetar flare. So I will be agnostic about the composition of the pre-shock wind for most of what I will be saying, even though most of the results that I'm actually presenting are more appropriate for an electron-positron, composition. And as the shock is produced, the argument is that, as I will try to convince you, that at the forward shock, the FRB is produced by a mechanism that is called synchron maser instability. So the basic properties of the shocks that potentially could produce the FRB are that the shock is ultra-relativistic, so the Lorentz factor of the shock much larger than unity. This is the relative Lorentz factor between the pre-shock medium and the post-shock medium. It's significantly magnetized. As I argue, the magnetization parameter, which here I'm defining as the ratio of the magnetic energy density to the kinetic energy density of the pre-shock flow, is over a unity or much larger than unity, and the shock is so-called transverse or perpendicular, which means that the shock magnetic field is actually pointing at you for a simulation plane that I'm depicting here. So the magnetic field is perpendicular to the shock direction of propagation. These shocks are actually not good for high energy particles acceleration, in case you are interested in non-thermal signatures associated with fast radio bursts. We do not expect, if these are the shocks that are acting in fast radio bursts, an associated non-thermal counterpart. However, they can produce coherent radiation via the synchrotron maser instability, and we'll now guide you through the 3 steps of production of coherent emission from the synchrotron maser. Step number 1. The magnetic field is compressed at the shock. The particles coming into the shock gyrate coherently in the shock-compressed magnetic field. Number 2, every freshly shocked generation of particles is forming a distribution in momentum that is a ring. This is a result of the gyration of the particles in the 2 components of momenta that are perpendicular to the magnetic field direction. So this is your population inversion. You have particles that are preferentially, due to the shock gyration, due to gyration in the shock-compressed magnetic field, localized at higher energies, and very few particles or 0 particles that are filling the hole at the center. And finally, the collapse of the unstable ring distribution results in the emission of electromagnetic waves. And this is our candidate FRB due to the synchrotron maser. So here is, in a one-dimensional shock simulation, the momentum space of the ring distribution that I just described in the 2 directions perpendicular to the magnetic field that is still pointing at you. And as a result of the collapse of this ring tends to fill up the center. You have the emission of a coherent train of electromagnetic waves that you see here with these wiggles towards the upstream, towards the medium ahead of the shock. So the emphasis now will be to quantify the properties of this escaping radiation and argue whether this can explain or not explain the properties of the FRB emission. Let me just summarize again the properties of the synchrotron maser instability, and then a few questions that I will address with the rest of my presentation. So naturally, the emitting particles have a highly anisotropic pitch angle distribution. If you're worried about the the efficiency of your maser in a quasi-isotropic state for the particles, this is not the case here. The particles are localized virtually in the plane perpendicular to the magnetic field, within an angle that is 1/gamma, at most, actually. The population inversion is naturally produced. As a result of the gyration in the shock-compressed magnetic field, you are preferentially putting particles on that ring. There is nothing at the center of the ring, so the particles have higher energies than what the center would have. And finally, the population inversion is constantly replenished. There are more and more particles coming into the shock. Every new generation of particle is established as a ring distribution, so you're constantly replenishing your maser capability. And the questions that we'll be addressing is, what is the efficiency of this process? What is the spectrum? What is the beaming? And what is the polarization? The basic setup of the simulation is something like this: upstream on the right, downstream on the left. The shock will be moving in the simulation frame. The simulation frame is the same as the post-shock frame, and we will always have a magnetic field that is perpendicular to the shock direction of propagation, a perpendicular shock. So for answering these 4 questions, I will use a reference FRB 190922. If you've never heard of this, it's because it doesn't exist. This is my fun, restless baby, born in 1909, 29. You should be 19. I don't know. No, it's true. It's good. Sorry. Yeah, I should remember my daughter's birthday, right? And of course, as you all know, if you have experience with your own kids, this plot actually means the dependence over time of your sleep deprivation, and the time is measured in years. Okay, so efficiency, or how much you should eat in order to increase by 1 pound. In 1D, so as I said before, the goal here is to establish the steady state nature of the maser. The maser needs to be sustained for a time that is much longer than the time related to one oscillation frequency of the maser itself. So what we're looking for in the peak simulation is really a steady state or quasi-steady state process. And here I'm quoting the efficiency of the maser as the ratio of the fluctuating magnetic energy over the magnetic energy density that the upstream medium is carrying into the shock. For different magnetization, as a reminder, this is the ratio of the magnetic energy density to the kinetic energy density of the medium ahead of the shock. So the two things that you notice from the plot on your left is that in all cases, we do reach a quasi-steady state. So this is good for making predictions for what the efficiency should be in the longer term, which may be as short as 1 millisecond. And the fractional amplitude of the fluctuation decreases with sigma. So for higher and higher sigma, you have a lower and lower delta B over B. And a point that will come back later to is the fact that this does not seem to depend for a fixed magnetization on the Lorentz factor of the relative Lorentz factor of the upstream versus the downstream. Here it's vary between 5 and 80. There is really no difference between the cases in terms of the delta B over B. Now you might argue this is all 1D. 1D is great, but it's not reality. So the synchron maser actually persists in two-dimensional simulations. Here the simulation plane is perpendicular to the magnetic field. The magnetic field is oriented towards you. You have a transient at early times, then the shock seems to be dead for quite a bit, and then it readjusts the separation between these two structures. I will come back to those later. And then you have the constant production of this electromagnetic wiggles produced and escaping towards the upstream. This is the FRB candidate in our 2D simulations. And the same occurs in 3 dimensions. This is 3D simulation that we recently performed with a magnetic field oriented as depicted there. The wiggles that you see here are once again a manifestation of the same instability producing electromagnetic waves in a 3-dimensional setting. So these are X-mode wave. The dispersion relation for the parameters that enter here is almost the dispersion relation for electromagnetic waves in a plasma. The experiment that we have tried is to stop injecting the plasma density in the upstream and see whether these waves can continue, and they do. So I would say these are also well-behaved electromagnetic waves in vacuum. So the efficiency in 1D that I quoted before, this is the summary plot for the efficiency of the synchron maser in multi-dimensions. So at low magnetization, I would say less than 0.3, 0.5, the 1D results are substantially different than 2D and 3D. And here I'm comparing also with recent results by Iwamoto. And the efficiency in 1D is a factor of 10 higher than in multi-dimension. This is because in multi-dimension you have additional physics. I will not enter into the details. The so-called Weibull instability can destroy the coherence of this process and so lower the efficiency of the synchron maser. However, for high magnetization, sigma larger than unity, the 2D, which is yellow and red here, and the 3D, which is green, is virtually the same within a factor of 2 of the 1D results. And the efficiency, which I'm casting here in the most appropriate terms as the ratio of the incoming energy into the shock to the escaping energy, the ratio of the escaping pointing flux to the incoming energy flux into the shock, drops with sigma as 1 over sigma squared. So these are the numbers you should take into account and consider if you want to match your best FRB model to observations. The temperature of the upstream plasma can play a significant role on the efficiency. These are recent results that Alia got. Essentially 2 points, the efficiency doesn't change by more than a factor of 2 if the temperature is less than 0.03 mc squared. However, if you're exceeding a temperature of kT over mc squared of order 0.1 or so, the efficiency drops by 1 order of magnitude, and virtually there is no maser for trans-relativistic temperatures. This is expected because with relativistic temperatures, the very nice ring in momentum space that I described before is broadened substantially, and then the center is already kind of filled up. And the true nature of the instability is at that point destroyed. I will skip this because I'm already running out of time. But I want to come back to a fundamental parameter of wave propagation. This is the so-called wave strength or Wigler parameter. It's a Lorentz invariant, which is defined in this way. Delta E is the fluctuating electric field of the wave, and omega is the frequency of the wave. And the Wigler parameter is such that particles have a typical transverse momentum oscillations in the field of the wave of order A times mc. So as the wave is propagating, is shuffling the particles around in the transverse direction, this is how much momentum oscillations the particle can have. So this implies that if A is much larger than unity, the particles will acquire in the transverse direction a relativistic momentum. And for FRBs, we typically expect A much larger than unity, up to a factor of few tens to 100. So what should happen in this case? First, most of the simulation that we have run are really not touching that limit. Here, A is of order unity for most of the sigmas that we explored. Depends a little bit on how you compute this Wigler parameter. It's a factor of 2 variation, but most of the results are for A of order unity, not much larger than unity. So will anything change if your wave is so strong to allow for or to force the electrons to move in the transverse direction at relativistic speeds, ultra-relativistic speeds? And two effects are expected. Number one, you expect that the wave will push the upstream plasma as a bulk. So the effect of the wave is actually to push against the upstream. The upstream will come in to the shock with lower speeds. The second point, as I described, you have internal motions which you might call heating of the upstream, which with a typical momentum that is also of order of AMC. So if A is much larger than unity, you're heating your electrons to ultra-relativistic speeds. So is this a problem? So for this, we ran a number of 1D simulations in a recent paper with Brian and Ben, and I'm summarizing here the results. The plot is a little crowded, so let me guide you through it. So the effects that I described, that I anticipated, are actually happening. So the bulk acceleration of the upstream does occur. However, the flux of particles into the shock stays the same because the plasma is also compressed. So it comes in with lower speed, but with higher density. So the flux of particles coming into the shock is actually the same. And the second point is that the mean energy per particle is also the same. And the longitudinal heating, which turns out to be the most destructive for the nature of the synchronous maser, is still under control, is still not significant. So the particles are effectively coming in with the same mean energy per particles and not with a large longitudinal dispersion in momentum, which will be deleterious for the synchrotron maser. So the bottom line is that the efficiency actually does not care about, at least in one dimension, which we have probed now, and we have some limited results for 2D as well, on the strength of the Wigler parameter, on this wave strength parameter, which for realistic FRB conditions should be much larger than unity. We can go now to much larger than unity, but the efficiency is virtually unchanged. So the wave is perturbing the upstream, but this is not changing the efficiency of the maser itself. Okay, so let me get to the second point, the spectrum. This is spectra that are obtained from 1D simulation of sigma 0.3, 1, and 3. There are three characteristic aspects that I would like to emphasize. The shock is acting as a high-pass filter, so only waves that are sufficiently fast such that the phase velocity is larger than the shock velocity can escape upstream. This is the reason for why this boundary, which is depicted with a yellow line, is shifting to higher and higher k or omega for larger sigma. The shock is moving faster if you are more magnetized. In the limit of very high sigma, in the frame of the simulations, the shock is moving with a gamma beta of order square root of sigma, which can be itself ultra-relativistic. So only waves with very high omega or very high phase velocity more precisely can escape. You also notice a typical shift in the peak of the spectrum. The spectrum peaks at higher frequency for larger sigma. And finally, the fractional spectral width is of order unity. But in some cases, you have features, line-like features that are even narrower than that. So this might be the reason for why some of the spectral features of FRB pulses are actually much narrower than delta omega over omega of unity. So we can benchmark these three diagnostics, these three signatures, with what we expect. The low frequency cutoff, determined by the requirement that the phase speed be larger than the shock speed, can be meshed with our expectation, the dashed line here. The peak frequency should increase with magnetization. It doesn't quite increase as the cyclotron frequency, the gyration frequency in the shock compressed field, as one would expect. I will spend one slide after that for why this deviation is happening. And finally, the spectral width is characteristically of order unity. But as I said, there are in the spectrum quite generically features that are narrower than delta omega over omega of order unity. So the physics of the determination of the peak frequency is a little bit different than what one would naively assume for the cyclotron frequency in the shock compressed magnetic field. And this movie illustrates what happens. So as I said, like nothing happens now. You see this cavity, the separation between these two high density structures, these two solitons at the shock surface changes. And when it reaches a certain length, then it starts radiating electromagnetic waves. So we find that the peak frequency of the emission is actually caring about the separation between these two density peaks in the shock structure. And it's sort of like a peak wavelength of the emission is a resonant mode for this cavity, is an eigenmode for this cavity. There are temperature effects on the spectrum too. Here is a case of a cold plasma for which most of my results are based on, and the orange is a case of a hot plasma, still high efficiency, over 1% or so, and a temperature that is over 10 to the minus 2 of mc squared. You see this two prominent line-like features, which have a delta omega over omega, much less than unity. So this is just a generic argument to say that you can have structures in the spectrum that are much narrower than delta omega over omega of order 1. And in principle, if they sweep through your observing band over time, if different frequencies are coming into your observing band at different times, you might have multi-pulses out of, in reality, a single shock, just because of the intrinsic structure of the synchrotron maser spectrum. Okay, I will not spend time discussing what this picture actually means and why I think this is related to beaming. If you have kids and you know what this phase means, you understand why beaming is particularly important right after this, but I will not spend time on that. So a point that I touched already upon, for these waves to be escaping upstream, they need to have a phase velocity in the direction of propagation of the shock that is larger than the shock speed itself. So in multi-dimension, in this case in 2D, this is setting a constraint for the relationship between the k vector along x and the k vector along y of the escaping FRB or candidate FRB. And this depends on the shock 4 velocity, the shock Lorentz factor, shock 3 velocity in the simulation frame. So this D here stands for the downstream frame. And as I said before, for a very high sigma, this product can be as large as, is expected to be square root of sigma, which can be much larger than unity. So the shock itself in the simulation frame is moving at ultra-relativistic speeds away from the post-shock frame, post-shock medium itself. And this causes that if you increase sigma, the range of angles over which the precursor emission is escaping ahead of the shock, and so it will be getting to the observer, is narrower and narrower. So you compare the case of sigma equal 0.6, in which you have a relatively broad emission cone, to the case of sigma 6, in which just because the shock is moving faster and the wave needs to overcome the shock, you're only confining your escaping waves to have almost zero transverse k vector. So this is more and more pronounced with higher sigma. The precursor is more and more beamed for higher and higher sigma. And finally, you have to tell me what this is. Yeah, so what does it stand for? This is clearly polarization, right? It depends which direction the antenna is moving. So I will conclude with one note on polarization. Polarization is trivial and wrong in 1D and 2-dimensional simulation with a magnetic field out of plane. And that's because in this configuration, you can only excite the so-called X mode. And this X mode, the extraordinary mode, has polarization such that the perturbed magnetic field, the wave magnetic field, is parallel to the background magnetic field. In 2-dimensional simulation with in-plane magnetic fields and in 3-dimensional simulation, you have another mode that will grow. This is the ordinary mode, the O mode, which has a fluctuating magnetic field perpendicular to the background magnetic field. So here the magnetic field is in this direction. It's not pointing towards you anymore. And the X mode is expected to have delta B parallel to B. This is what you're seeing here in the ripples in the upstream. And the O mode, which is seen here, not strongly, but you see the same fluctuations on a similar wavelength as a magnetic field perpendicular to the background magnetic field. So ultimately, one needs to do 3D to answer this. The presence of both home modes and X modes in principle can degrade the polarization. The X mode by itself will be 100% linearly polarized because you only have one mode. But here you have a competition with the O mode. So 3D simulations will be needed to answer this. So this is a preliminary plot on the ratio of the power in O mode versus X mode as a function of the magnetization from 3D simulations, as I said. So the ratio is over unity for relatively modest magnetizations, and it seems to drop. This is only a lower limit, potentially as 1 over sigma, tentatively as 1 over sigma for higher and higher magnetization. So if one were to extrapolate this trend with the numbers that are given here, one would expect 90%, 99% or higher linear polarization for a magnetization of 30 or higher. And 90% polarized, as I'm showing here, for a magnetization of 3. So the synchrotron maser has the possibility of being very highly polarized, linearly polarized, but only for sufficiently high magnetizations. And I will just make one quick point in case anyone is interested in non-Gaussian features in the fluctuations. The fluctuations are fully Gaussian, so if you have the full available voltages for your measurements, this is what we generally expect, no deviations from Gaussian. And I'll be happy to discuss more about the synchrotron maser physics in the electron ion case, which I have completely neglected here because it's significantly less understood and studied. But with that, since I'm out of time, I will conclude. So we are arguing, and this is sort of like within the framework of the general relativistic shocks in around Magnetar's model that Ben and Andrei have already discussed yesterday. We're thinking about Magnetar flares driving relativistic shocks, and synchrotron maser at these shocks producing the FRBs. And this is sort of like a number of conclusions that are also coming from Ben's and Andrei's presentations yesterday. We do have linear polarization if the magnetization is sufficiently high. The polarization angle, if it retains the memory of the rotation axis of the magnetar, should be not varying too much. And then the other points is, generally speaking, narrowband gigahertz bursts are expected, the downward frequency drift as the shock is propagating out in the wind of the magnetar, and potentially a counterpart at optical X-ray and gamma ray frequencies just due to the shock-heated electrons right behind the shock. And with that, I will stop.